Years of teaching A-level physics has convinced me that big M is one of the biggest stumbling blocks in the whole course. Ask a student if they understand gravitational field strength. Of course, they reply confidently, but get them to unpack what the statement means and that confidence just disappears down through the floor. If you give them an exam question, it's going to disappear in a puff of smoke 9 times out of 10. Why is this? Well, this video aims to strike at what I believe is the root of this problem. What is big M and where has little m gone? Welcome along, physics fans. Gravitational field strength is given the crazy value of 9.81 newtons per kilogram on planet Earth. This means that for every kilogram of mass there will be a force caused by gravity of the Earth of 9.8 newtons. So for example, this 2 kilogram bag, if it's left on the floor somewhere, not only will it get chewed up by the dog, but it will have a weight of 2 times 9.8, which is 19.6 newtons. Simples. And that is about as far as you go in normal school physics. Now we're going to dig a little deeper. The formula for gravitational field strength at first sight does appear to be really simple. We have big G as the gravitational constant, m as the mass, and r as the separation of, well, the separation of what from that mass. And this is one of the things that students get concerned about. Just what is m? What is this mysterious big M in this equation? Some students refer to it as M1, and that's okay. And others will say, well, it's a capital M, so it's the big mass. Yeah, but what is the big mass? It's pretty obvious, I suppose, if you've got a satellite going around the Earth. But what if you've got 2 stars orbiting each other? What's the big mass then? The idea of big mass just doesn't cut it. It's not precise enough. In order to really work out what's going on here, I need to pose a different question. And that question is simply this. Can you have a gravitational force if there is only one mass? Now, most of my students that I ask this question to, and I must say it's normally quite entertaining for me, will immediately say, yes, of course you can. And then as they reflect a bit more, and as I help them reflect a bit more, they begin to realise that no, you can't have a force if there's only one mass. Newton's third law tells us that every force has an equal and opposite reaction force acting on a different object. And that second half, the acting on a different object bit, is often ignored but is really important. It's acting on a different object. In other words, there are 2 objects. So the answer is clear. You can't have a gravitational force if there is only one mass. The name for gravitational field strength includes the word strength. And when you think of the word strength, you automatically think of forces. And indeed, gravitational field strength is a force. But how can it be a force if there's only one mass? The answer to this little puzzle lies in the proper definition of the word field. So for example, a gravitational field is a volume of space around an object where there is the possibility of a force if you introduce a second mass. Did you notice the word possibility there? Sometimes you'll see that written as potential, but I prefer possibility just to keep things simple. So if there is the possibility of a force, that means there isn't a force until you introduce the second object. When thinking about gravitational field strength then, the capital M in the formula is the object that you are considering. But the second mass, which isn't in the formula, we'll talk about how it goes in a moment, is always set to 1 kilogram. And this is where the idea of the test mass, or more commonly unit mass, comes from. Unit, of course, being a word for 1, in other words, 1 kilogram. So gravitational field strength is really the strength of the force acting from object M on 1 kilogram as you move it around in the field created by the object capital M. Simples when you look at it like that. I like to explain to my students that there's a really close link between gravitational field strength and Newton's law of gravitation, which is written down here. If you take Newton's law of gravitation and divide it by small m, then the m goes onto the bottom, the m's cancel out, and we are in fact left with the value of the force of m acting on 1 kilogram. Ha! Gravitational field strength. So really all we're doing is dividing by m. And that explains where the newtons per kilogram comes from in the units for gravitational field strength. One last thing to add. Gravitation, as you know, is an attractive force. but I bet there's a repulsive version of it somewhere. We just haven't found it yet, or at least not in the public domain. But I digress. Gravitation is an attractive force, and by definition, physicists have decided that all attractive forces are referred to as being negative. This means that sometimes you will see these formulas with a negative sign in front of them. Now, to be honest, that doesn't really make a huge amount of difference when you're talking about field strength, but it's going to make a massive difference when we talk about gravitational potential. I'm going to do a couple more videos on this, and the next one is going to be all about how do you find this mysterious point between two masses where there is no resultant gravitational field strength. So look out for that one. Bye for now, physics fans.